Good morning or good afternoon. See some people have entered the chat already. So I just said as well, we'll start in a couple of minutes. Just waiting for the participants to join us now. From Brazil. So I think we'll have participants today, at least registered, over 200 from, I think it was 50 different countries. So very nice to at least see you all virtually. All right, we'll give it 2 more minutes before we start, and welcome everyone. Good morning, and welcome everyone. Welcome also to our speakers, of course, who you can see on the screen here. I'll get to the introductions right away. All right, we're almost ready to start. I think we'll make 1 more minute. So as I said before, we have about 200 people who have registered for this meeting from over 50 countries, all now streaming in. So I see people joining us from Brazil, Indonesia, from Europe here, of course, together with our speakers. So welcome everyone. All right, it's 2 o'clock, so I think we can start the meeting. And I see also joining us from South Africa. We have participants, as I said before, from over 50 countries joining us today and still joining us at the moment. So welcome everyone. Welcome also to our speakers for today. So my name is Willem Damore. I'm the Deputy Director at the JPI Oceans Secretariat. Hope you can hear me all. Yeah. For those of you who don't know, JPI Oceans is a European platform for the coordination of marine and maritime research. So our members are research ministries and funding agencies that pool their resources to develop what we call joint actions. And these actions can range from expert groups to, for example, joint calls for research proposals. The latter is what led to this project. So together with our colleagues from JPI Climate, we launched a joint call for research and innovation proposals back in 2019, which led to 4 research projects which started their work back in September 2020. And one of these projects is the project which is going to present to you all today, the CE2COAST Project, in full downscaling climate and ocean change to services, thresholds, and opportunities. The CE2COAST Project focuses on oceans and climate using observations and Earth systems models to address global scale climate change challenges. And today we have with us 4 speakers who will present to you the project to you. And before I introduce them, I'll just sort of briefly address the housekeeping rules for today. So what we'll do is we'll run through the presentations. If you have questions, you can ask them in the Q&A, rather in the Q&A than the chat. And we'll address those questions then after we have run through all presentations. So with that, I think we are ready to start. So our first speaker for today is Richard Bellaby, the coordinator of the CE2COAST Project, Chief Scientist, Ocean and Climate at the Norwegian Institute for Water Research, which is based in Bergen in Norway. Richard is also director of the Skleck-Niva Center for Marine and Coastal Research in East China in Shanghai, and as I said, the coordinator of the project. So, over to you, Richard.
Thank you very much. I'll just share my screen, and I hope that you'll soon see the opening page. Is that correct?
Yeah, but it's not yet in presentation mode, so you will have to swap displays.
Yeah, I see. Yes, there we go.
Yeah, correct.
Great. I will start then. Well, thank you everybody for joining us on this Friday morning, afternoon, evening, depending on which part of the planet you are joining from. As said, I'm very happy and honored to be the coordinator of this project. I have slightly changed the title. The title was rather ambitiously Coastal Climate Change. And there are two reasons for doing this. One is that in 20 minutes, it would be unreasonable to present all the relevant changes to all the interested parties to this presentation. And two, the whole ethos, the emphasis of the CE2COAST project is that it is not scientist-led. It is a co-production. And therefore, we are delivering knowledge to the best of our ability with the modeling tools and the observational tools to the requests of the stakeholders who we communicate with. So we do not presume that a particular region, there is a particular aspect of coastal change which we will press upon them. So I'm just going to give you a very brief introduction to some of the changes which are occurring globally and in the coastal regions. But mostly, I'm going to show you how we are addressing this co-production of knowledge, what process we have adopted and developed along with stakeholders to reach the goal of delivering targeted, relevant climate change products or knowledge products, which are understood, usable, and importantly, highly relevant to the different stakeholder requirements. Now, most people understand that coastal change from what they see on their doorstep or they see in their daily lives, in their business, and also what they see in the press and on the TV. And you see the results of climate change. You see in these three, say, very random examples of ongoing challenges to coastal systems, whether it be coral reef die-off, whether it is the increasing intensity and frequency of harmful algal blooms, or whether it's the increased erosion that we are seeing in many parts of the world. But that does not give any understanding of what are the causes and how these different stresses on the system, on coastal systems will change in the near to mid-term future. We need this information because we have to advise on good stewardship, on methods to mitigate climate change, i.e. promote systems which can absorb more carbon or produce or also adaptation measures which can ensure resilience and, importantly, with the 2030 goals is to manage a system to have maximum yet sustainable productivity. So this project is addressing these tasks over many different regions. I'll start off at the global scale. There's a very good paper by Nikki Gruber, just been released in Nature, and it shows how pressing the knowledge is on climate change. You see, well, this is an example of how temperature and ocean acidification, here addressed by the hydrogen ion concentration or oxygen, has changed. And remember, this is not a future IPCC report scenario at the end of the century. This is now. And you see here that this is the surface and this is at 200. So from the beginning of the Industrial Revolution to today, you see the number of extreme days per year of temperature, of acidification, and in the subsurface, and this is actually quite near the surface, but in the subsurface, the increase in oxygen concentrations which are below thresholds for certain marine life. So the extremes have become the new norm. There are 50 extreme days per year globally within this system in the surface, and there are 365 days a year of ocean acidification extremes. These are extremes which go over the tolerance levels, but also they are outside the natural variability. So we're outside most of the variability from which most of the species that are in our ocean, in the ocean, have evolved through. So there's obviously a very global picture, but the coarseness of this model does not give opportunity to focus in on the local level. And Moma will talk about how we are going around improving this for the coastal system. So these are just three of the major biogeochemical and also thermal studies that's shown that these variables are changing very quickly, and all three are critical to marine life. But when it comes to the local level, climate change is much, much more than what is generally understood. Climate stresses co-occur with local stresses, and these local stresses can also be both climate stresses like increased rainfall and river flow into the ocean, increasing sediment flow into the ocean, organic material into the ocean, but it's so much more. It's ocean darkening, it's ocean freshening. Then we have to bring in microplastics and all these extra stresses which are not normally viewed on as a package when it comes to understanding the combined multiple stresses on a coastal system. And these extra stresses are generally more of concern to our stakeholders than many of the traditional ones which we as climate researchers would traditionally come to from a climate research point of view. And importantly, climate change knowledge is needed at the relevant scales. We need to get right down to where that aquaculture unit is. We need to get down to where that important fishery is, where that coral reef system is, etc., etc. So we need to really downscale these large global changes and combine them with local stresses. So we were very fortunate to get the Sea2COAST project funded. As was said, the title is Downscaling Climate and Ocean Change to Services, Thresholds and Opportunities. Now the latter part, thresholds, we have a work package which is identifying or identifying thresholds for the different ecosystem providers or the service providers. But it's also an optimistic project, that it's not just the doom and gloom of a traditional IPCC report in the newspapers. It's looking for opportunities. It's looking to understand downscale climate change projections to promote good investment, good management, to anticipate change and be ready for change, and actually, in some cases, gain from change. So who are we? Very briefly, we are a pan-European, all the way from Iceland and Norway in the north, through Belgium and France, Ireland, Latvia, in Italy, and Portugal, including the Air Centre, the organisers of today's Networking Friday meeting. We have two main hypotheses. One is very much the scientific one, which I've just described, is to use and optimize dynamic downscaling ocean modeling approaches to provide improved scientific understanding and more realistic and accurate local projections. But as I said, equally important is that this co-production approach, incorporating stakeholder input and local observations, can provide improved and better focused knowledge and management at appropriate scales. Now, I shouldn't assume that you haven't understood what I've talked about, but seeing we've been here before, one of the most important challenges that we have to address is the translation of the scientific method and terminologies. So when I say translated, this is not from English to French or whatever. It's to communicate the terminologies, thresholds, tipping points, etc., the different species, the different terminologies, the different approaches, so that the message is understood and therefore received. We have a very circular, a very iterative approach where stakeholders are at the center. We can start right at the beginning. We define the service. We come together with them. We communicate the stresses. They can inform us of how the system has changed through their eyes. Then we identify which ecosystem service we will focus on. We then gather historical data. We take new measurements. We can also have community sampling in certain cases. The combination of this ecosystem service and stresses, we can evaluate the ecosystem response and give early stage advice to investors, for example. The ecosystem response data, the thresholds and tipping points, are combined with the projections as well as the data helping the projections. We then develop new climate scenarios, which are again discussed with the stakeholders. The stakeholders then can take action. They can invest in something else. They can, certainly the policy people can base their local regulatory process on some of our information. But then it's circular. We can start again. And you can actually begin anywhere in this circle, but this is the approach that we are taking. One of the challenges we have to admit is co-production in action. Pre-COVID, and this was pre-Sea2COAST, this was actually a Norwegian coastal climate change project. We were very active. We had many meetings, very physical meetings. It's very good to gain the trust, and also to gain the local knowledge is much easier at a face-to-face level. But after COVID, we still have managed to reach out to local stakeholders, but also to international policy organizations. And I just want to emphasize this co-production. It's central now to a lot of the research, certainly the research approach, which is coming through the European Union and through national research groups. It's this deliberate process of producing knowledge through collaboration between users and experts to ensure relevance and legitimacy. This is really what is at the heart of our project. I think, yeah. We, as well as the funded team, we have collaborated with many, well, at the global scale, with many of these leading organizations in ocean observations, in modeling, and also stakeholder participation. And through this joint collaboration, this is presently the regions which we are which we are studying. So you can see that obviously there's as is expected from a European funded project, there is a focus on Europe. There's also a very good overlay of different modeling groups, which facilitates comparison. But you see that we also have representation in South America, which Veronique will talk about. We have a group studying the Great Barrier Reef and also around Tasmania. And we have a team in Shanghai studying the East China Sea. The ocean and ecosystem services which were agreed at submission are included in this figure. So we will document changing CO2 uptake and carbon sequestration, so relevant to the NDCs towards the Paris Agreement. We are studying primary production and mesopelagic production relevant to the fisheries. We're studying coastal change directly related to aquaculture processes. We're studying current changes and coastal protection. And there is a strong stakeholder participation from tourism and recreation. And there is a study on offshore installations. The main pressures which we are studying, actually, I should have added to this, but I have COVID, so I haven't had time this week to add to this. But pressures are ocean acidification, ocean oxygen, nutrient supply, warming, river inputs, so freshwater, sedimentation, light fields, the wave climate, upwelling, circulation, sea ice cover, and particulate organic matter. This is our workflow. I'm not going to go too much into the details of this, except this is another way of showing it. Actually, the next talk is mostly on work package 1, looking at the state variability and trends of the historical and new project data which has been accumulated. Then we have the Earth system models which have been evaluated at regional level for their skill. That is then, the knowledge about this decides on which of the Earth system models we will use to force the regional models, which then will have already developed or the optimal approaches to how to downscale the information down to the service providers, which are here on the left. And then we are very underway now with determining the thresholds and tipping points for many of these service providers. And then certainly part of this talk, well, this talk is part of this work package, which is very much communicating from the stakeholder level through the general public, through the scientists, and also we have a remit from JPI to provide knowledge for future coast of marine policy. So I see I only have 1 minute left. I have to thank our funders. And then I'll finally finish with an open invitation to you, either from the stakeholder level or from the scientist level, to join the team, to contribute to our stakeholder meetings, to work with our observationalists and modelers. You can contact us either through the Twitter here, or the information about contacting me or any of the other people in the team is through our website on CE2COAST.com. So with 5 seconds to go, I thank you for your time.
Thank you very much, Richard, and thanks a lot also for joining us while you're still recovering. Very impressive to see the global scale as well of the project, and seeing the geographic variability there. We won't have time for questions now. We will have questions after all presentations, so we'll go immediately to the next presentation. The next speaker is Véronique Garçon, who's currently the co-chair of the Scientific Steering Committee of the International Ocean Carbon Coordination Project and of the GBC GOOSE panel. Véronique's research teams aim towards understanding and quantifying processes governing fluxes of carbon, oxygen, and associated biogeochemical geochemical elements in the ocean. So I'll give the floor to you, Véronique.
Okay, thank you. I'm sharing my screen. Do you see it?
Yes, so we would just need it in presentation mode, ideally.
Is that okay?
Yeah, so perfect.
Okay, great. So good afternoon, good morning, good evening to all of you, wherever you are in the world. So it's my pleasure to continue presenting CE2COAST work after Richard's introduction to coastal climate change through the lens of our project. So I'm co-leading work package 1 with Solveig Olavsdottir from Iceland. And this work package is aimed at assessing the mean state variability and trends in our CE2COAST regions. And today I will focus on one of those regions, the Southeastern Pacific, the Humboldt system. And it is work done in collaboration between our team in Lagos, Toulouse, France, CEOASA in Chile, and IGP Peru. So I've chosen to show you this map of all available observations and platforms as of June 2021, which is produced by the Global Ocean Observing System, GOOSE, in their report card 2021. So it shows all Eulerian and Lagrangian platforms. We see the ship tracks, we see the dots for the fixed mooring, and a multitude of small dots, which are not, of course, to scale. And it seems like a dense network. But when you're restricted only to the little Lagrangian platforms, in light blue, you have the surface buoy, which drift with the surface current. Dark blue are the Argo floats equipped with physical sensors. And the pink one are those with, in addition, biogeochemical sensors. So as you see, the density gets a bit weaker. And I've added on top of it our CE2COAST region, which cover all Europe and shelf seas, as Richard mentioned, the Arctic, the North Atlantic, the Black Sea, the Med Sea, and the Humboldt. And in this region, the coverage is good, sometimes it's not as good for observations. So we estimated the mean state, variability, and trend of all existing physical and biogeochemical variables in our region. So meaning temperature, salinity, oxygen, nutrients, chlorophyll A, carbonate chemistry system. So for CE2COAST region, the length of the time series falls short. To be able to truly refer to a trend, we rather documented variability on internal time scales on data spanning 20 years or less. But for certain sites, we have quite long time series, up to 60 years, so we can really refer to trend. So I'm showing here a few examples. For the Black Sea, for instance, we've looked at the oxygen trend based on Argo floats. For the Med Sea, we looked at the archives, the satellite archive for SST and chlorophyll A. This is just an example. There are other variables, of course. We did that also for the Northeast Atlantic. For the Nordic Sea and Arctic, I'm presenting here a time series of nutrients over 50 years of data. And in the Humboldt, the time series to be shorter is 8 years from a mooring close to southern Chile. So we have done that for all existing information that exists in our CE2COAST regions. So we use this observational regional data set to deliver empirical understanding of the state variability and trends of ocean climate, biogeochemical, and ecological indicators, which are useful for model predictions. So in addition to the existing database, we were entitled to acquire new observation. But as you all know, the COVID pandemic struck just before our project started in September 2020. So some of the cruise planned had to be delayed, postponed, some were canceled, but some took place. And despite COVID, we managed to deploy new instrumentation. I'm showing here an example of an Argo deployment in May 2021 from the Tara ship of Chile. And it's part of the French CEPICAF and Chilean CLAP and the JPI CE2COAST Project efforts. So I'm showing here a vertical profile of oxygen, which is typical of the region. You have a very strong oxycline, then you have a core of very low oxygen water between 200 and 400 meters, and then you have the profile increasing again. So within CE2COAST, as Richard mentioned, we look at pressure that represent challenges to both open and coastal system. And here the pressure and the consideration in the Humboldt clearly is ocean de-oxygenation. And we will look with stakeholders, fishery, aquaculture farmers on the impact for the ecosystem services. So as you all know, the ocean is losing oxygen. I've put in here the red dots, which are the coastal site. The number of hypoxic site has been multiplied by a factor of 10 over the last 50 years. The blue dots are the oxygen minimum zone, and their volume has quadrupled over the last 50 years. And overall, the global ocean has lost around 77 billion of tons of oxygen over the last 50 years. So in the OMZ core, that yellow profile I just showed you, it is extremely difficult for organisms to breathe. And any deviation from the normal level of oxygen can really represent a daunting challenge for the species that have been adapted already to those very low levels of oxygen. So there is not much oxygen in water as compared to air. And animals need to work hard to extract it. 1 liter of air is 1.3 gram of mass, and it's 0.3 gram of oxygen. 1 liter of water is around 1,000 grams, and it's 0.008 gram of oxygen at saturation on the surface. When you go down the water column, it's even smaller. So it means that the difficulty of organisms to breathe normally will have an impact on their metabolism, reproduction, growth, fecundity, weight, and mortality. So basically, it will have a tremendous impact on the marine ecosystem structure and functioning. And this is key for addressing ecosystem services. So we need to understand properly that pressure. And what are the causes of oxygen? Of course, ocean warming, the warmer the water, less oxygen, increased stratification, and reduced ventilation. And in the coastal system, nutrient loadings through continental runoff will reach coastal waters and leading to eutrophication and increased consumption of oxygen. So let's go back to the Southeastern Pacific. And I'm showing here a schematic of the mean circulation. So this is the equatorial system. We have the equatorial undercurrent, the two Tsuchiya jet that are very key for the dynamics of the OMZ. Since they supply water of different oxygen content. And the two Tsuchiya jet here are carrying low oxygen water. That system feeds the Peru-Chile undercurrent, which is flowing poleward along the coast of Peru, Chile. The red arrow here represents the thermocline ventilation. So that is in its conceptual view, the subsurface equatorial transport of water masses through potential vorticity conservation from the surface in the mid to high latitudes. And the blue arrow here, the wiggle, represent dipycnol mixing. So in addition, the Southeast Pacific OMZ is strongly influenced by variability in the central equatorial Pacific Ocean, the ENSO variability, which modulates the coastal upwelling driven by the divergence in Ekman transport and mesoscale activity, which is illustrated here by the cyclonic and anticyclonic ADIs. So this is a figure from a nice review by Pitcher et al. Published in Progress in Oceanography last year, a review on all low oxygen systems in the world ocean. So I will show you how we can use regional observational data set to deliver empirical understanding on variability and trends in the CE2COAST region simulated by the Earth system model. So I'm showing here an ensemble, the OMZ volume anomaly from an ensemble of SEMI 5, 9 of them, and SEMI 6, 8 of them, from 1850 to 2100, and we are considering water with oxygen concentration below 60 micromolar. So the time series here is centered by removing the historical period 1950 to 2005 in these little inlets. So the CARS is the Atlas from 2009 with a dash line, and all the other ones are all the different models that we considered, so quite a widespread. The very thick dash line here represent the mean, and the blue area is, the blue shaded area is the standard deviation. So what do we note? We note a huge spread in projection. Some model project an expansion of the ONZ volume, some a contraction, and some just steady state. So we then computed for this ensemble mean of those Earth system model, the linear trends of oxygen. So we represent here a zonal section at 100 meter, and the two right panel, it's a section at 12 south and a section at 30 south. So it's as a function of depth. We're here on the coast going westward. So what do we see? We're looking at trend in micromolar of oxygen per decade. The white stipple line with a white star represent region where we have less than 80% agreement between models. The black line here is the 45 micromolar contour at 100 meter and the dashed black line at 200 meter. The red line here represents the zero net trend. So what do we see? We see that we have model being consistent with positive trends, meaning reoxygenation, very close to the coast of Peru and northern Chile. And of course, a wide region, a very wide region where we have de-oxygenation trend consistent in between all models. So what is important to note here, we've put here the E-index pattern, which are diagnosing ENSO variability, according to Takahashi et al. 2011. So the red one is for the present time and the blue one for the future scenario. And we see that the positive trend at 12 south, at least, are in between those E-index contour, suggesting a possible link to the ENSO-like variability. And when we look at the two vertical sections, we see that the positive trend are really in the upper bound of the OMZ core, close to the oxycline, both at 12 south and 30 south. So we've regressed the oxygen onto the E-index pattern, and this is the same representation. We have a zonal section at 100 meter, a vertical section at 12 south, and a vertical section at 30 south. So what do we see? We see that the ENSO impact on dissolved oxygen ensemble mean is more concentrated in the equatorial region, exhibiting oxygenation during the warm ENSO phase, and especially at the coast. So it positive value indicate where oxygen concentrations increase during an equatorial Pacific ENSO event, which is almost everywhere along the coast, and in the upper limit of the OMZ core as seen on the two vertical sections. So if we think of an emergent constraint framework, the ENSO-induced oxygen filtration could be used as a predictor of the long-term change in oxygen here. And this is supported by the fact that SST climate change pattern in the Southeast Pacific has Equatorial Pacific ENSO-like pattern. So what we did is to extract a time series in that rectangle, black rectangle in the upper bound of the OMZ core, and compute linear regressions between the E index and the oxygen internal anomalies. And we did that for each of the model that we looked at from CEMIP 5 and 6. So the upper row is at 12 south and the lower row is at 30 south. So for each model, we computed a regression. So the next step is across a multimodal ensemble to look at the correlation between the internal sensitivity of oxygen to ENSO-driven SST variability and the long-term sensitivity of oxygen to oxygen climate change in the 21st century. So what we did is to cluster the ESM linear regression into one vector for the historical run and calculate the correlation with the analogous future scenario coefficient vector. And this is what we did here, and we found a positive strong correlation of 0.6. So here it's where the observational constraint come in. So in the Humboldt, there are not so much data. I show you the time series in my earlier slide at 30 south, but it's kind of short, it's 8 years long. So we use the one at 12 south, which is a coastal station presented in Greco et al. 2017. And this is the line we introduced here. The time series is 15 years long, so we can start assessing internal variability quite well. Interesting to note is that model with higher internal oxygen sensitivity in SST anomalies in the Eastern Equatorial region in the historical simulation consistently project also great oxygenation in the upwelling center of Peru here at 12 south, within the oxycline, which is the upper OMZ per degree warming in the 21st century. So these lead me, so you see that the more observation we can have, what we did also, I forgot to mention, we added here in blue output from a regional model we have developed in the region and validated in the region to put another constraint, but of course it's model output, it's not observation. So the more observational constraint we can put from the oxygen ENSO sensitivity, the more we will be able to infer oxygen climate change impact with confidence. So that leads me to enforce the need of a coordinated global open and coastal oxygen atlas, go to that, which will interact with GDAC and with users, stakeholders through a web portal, and to do that with a transparent quality control and quality flooding. And the goal is really to include all the Winkler titration oxygen measurement with CTD oxygen sensor, the Argo sensor, the glider sensor, mooring emergent, I'm thinking here of marine animals and benthic platforms. And the idea is to produce data climatology and data product that can be used by the international community. And this is a key step since oxygen observation are really key to better constrain the long-term Earth systems model projection and better evaluate their impact, the impact of this pressure on the ecosystem services. And this is really the heart of the CE2COAST project. I'm just showing here one of the systems, but this is work undergone in all the CE2COAST regions. So to briefly wrap up, across the multimodal ensemble, we've shown we have a strong positive correlation between internal sensitivity of O2 to ENSO-driven SST variability and the sensitivity of oxygen to climate change in the 21st century. There is a strong uncertainty in ESM long-term projection. This is true for CEMIP 5 and CEMIP 6. Of oxygen sensitivity of the upper bound can be used as a predictor of that of its long-term trend, with the possibility to have an emerging constraint associated to the Southeast Pacific OMZ. And when we apply observational constraint to the multimodal emergent relationship, we can derive estimate of the long-term sensitivity of oxygen to climate change. And the more observational constraint we will have, the better we will be able to constrain the projection. And with that in mind, I'll thank you for your attention, and I'll leave the floor to Mome, I think, who is next. Thank you.
That's right. Thank you very much, Veronique. Some very interesting results there. And I'm sure we'll get to it later in the Q&A session after all presentations. So I'll give the floor to Mome Buitenschoen indeed. So Mome is Deputy Director of the Ocean Modeling and Data Assimilation Division and lead scientist of the Earth System Modeling Research Unit at the Euro-Mediterranean Center on Climate Change. Quite a mouthful. So within CE2COAST, Mome is also co-leader of the work package 2, which focuses on Earth system models at regional scale, and as such responsible for the development of the modeling system covering the European sea basins. So Mome, I'll give the floor to you.
Thank you, Willem, and thanks to the audience for joining this session. We're glad to have you here. Let me just go to the first slide. So this talk is about building capacity for modeling the marine environment in European seas under climate change. So I will give you a little bit an overview about the regional modeling activities that are going on in CE2COAST. And I've prepared this talk. Oh,
sorry, Mome,
yeah.
Can you just
Full
move
screen.
into, yeah, exactly. Thank
Sorry
you.
about that. And I've prepared this talk with inputs from my colleagues, Phil Walhat from NIVA and Marie-Laure Grégoire from the University of Liège, and actually all of the other modeling teams that are involved in CE2COAST. So thanks to them as well. I'm going to open with a statement from the last IPCC, not the last, but the special report on ocean and cryosphere from the IPCC. And the statement is that coastal ecosystems are affected by ocean warming, including intensified marine heat waves, acidification, loss of oxygen, salinity intrusion, and sea level rise in combination with adverse effects from human activities on ocean and land with high confidence. And impacts are already observed on habitat area and biodiversity, as well as ecosystem function and functioning and services. So this is really the motivation of our modeling work here within CE2COAST, the statement that underpins it. And there's actually another statement in the same report, or actually in the chapter on ocean, which is this one here, which is, I'm going to read out as well, and then I'm going to stop reading. The impacts on ocean ecosystems, it says, and human societies are primarily driven by regional trends and by local manifestations of the global scale changes. At these smaller scales, the temperature, acidification, salinity, nutrient, and oxygen concentrations in the ocean are also expected to exhibit basin and local scale changes. However, the ocean also has significant natural variability at basin and local scales, with timescales from minutes to decades and longer, which can mask the underlying observed and projected trends. The impact of multiple stressors on marine ecosystems is one of the main subjects of this chapter, including new evidence and understanding since the last assessment reports. The most severe impacts of a changing climate will typically be experienced when conditions are driven outside the range of previous experience at rates that are faster than human or ecological systems can adapt. So this really manifests pretty well the problem we're facing and tackling with the modeling work here at CE2COAST. So already at a system level, the trends, the same trends that we find globally exist at regional and local levels, but to different degrees, and at times even in different directions. And on top of that, those regional and local areas have an inherent variability that masks these trends, which doesn't mean that the trends aren't there. It just means they are very much harder to detect and identify, which is the dilemma of the modeling work that we're facing. So there is a strong need for detailed and regional and local information and knowledge to inform mitigation and adaptation strategies, which is the other key message of these two statements combined. So if we go a little bit more towards the modeling then, if we look at the global climate models, and I've just put up a couple of examples here, the problem with the global models, or the Earth system models to be more precise here, is that they have a relatively low regional affordability compared to their global trends. And that is due to uncertainties and biases they have at the regional and local level. So what you see here in the middle column is a work of last year, which I've contributed to, on primary production. And you see on the top of it, the biases at the regional level between the models, and you can see that they are not the biases, sorry, this is the trends, the future trends. And they go from -6 to +6 at regional level and at this global scale. So then if we look at the spread across models, which is the other two figures below, one is the standard deviation and one is the total range, so minimum model to maximum model. You can see that there are substantial differences between the models. So if we look at the total range, that is essentially 5-fold the actual climate change signal at regional level at top. But what you can also see is that they are limited to certain areas, or at least they are much stronger in certain areas than others, which are the Indo-Pacific and the North Atlantic, to be a little bit more specific. On the right-hand side, you can see that the same applies essentially to other variables. So here you have an interquartile range between the models involved in the study of Koski et al. 2020. And you see several variables, not only primary production, but also nitrate, oxygen, pH, and SST. And what's important to note here is that also there, for these variables, you have substantial spread across the globe in different regions, but also they are the spread in the big spread in one variable doesn't translate necessarily to big spread in another variable. So you can see that, for instance, the biggest spread you find for temperature is in the high latitudes. For pH, similarly. For primary production, as we've seen before, it's in the equatorial upwellings. For nitrate, you find it in the Peru-Chilean upwelling that we've just been looking at in Veronique's talk, and also in the North Atlantic, and again in the Arctic. So it's a very heterogeneous picture of uncertainty that needs tackling by dedicated downscaling efforts at the regional level. And that's what we're trying to do within CE2COAST here. So just to give you a couple of examples from the past, how we've been tackling the problem to inform mitigation and adaptation strategies with regional modeling systems. So this is not direct CE2COAST work, but it's done by CE2COAST team members in the past, and we will have similar initiatives going on within CE2COAST. And the first example I'm going to give here is about Iconization in the Mediterranean Sea, which is a paper by myself from last year. So we're tackling here the Mediterranean Sea because it is a hotspot of climate change. It provides a dense shipping network of vectors of lime discharge, which is a convenient way to transport lime over the ocean at low energy and financial cost. And it is a semi-enclosed basin with limited ocean exchange to the outside oceans. Which makes it favorable for a regional application because you have less lateral losses of your initiative, of your application. So very briefly, the outcomes, if you're more interested in read the paper, you will find it in the references later. Very brief, the outcomes we've had here from this work is that alkalinization in principle allows for substantial increase in CO2 uptake of the sea. It counteracts acidification. But the system response, again, even at the regional level, is very heterogeneous and depends very much on the underlying physical features and the background distribution of alkalinity. So I haven't shown this here, but if you look at the picture at a basin scale level, you will find lots of dots of high efficiency and low efficiency of the alkalinization process. So you can optimize the process a lot by alkalinizing more in certain areas rather than others. For instance, it is not very convenient to apply alkalinization in estuarine areas of river discharges where the background alkalinity is already very high, so the buffering capacity of the water is already very high, so you're not changing it much by adding extra alkalinity. On top of that, of course, the ecological implications of such an intervention have to be assessed. What happens to the system if I drastically increase alkalinity of the water? That, of course, we couldn't do at this stage with the modeling work that needs some serious experimental studies. Another example is here for the North Sea. So in this case, the offshore wind farm footprint on organic and mineral particle flux to the bottom was investigated by Ivanov et al. 2021 from Marie-Laure Grégoire's group in University of Liège. So what they did on top of a biogeochemical and physical projection, again, they applied a wind farm scenario, which you can see in the picture with an example of one of the scenarios they applied. In this case, it's the spatial distribution of annual change in total organic carbon deposition under one of the scenarios, as I mentioned. And their main outcomes in this work were that the main impact of wind farms is actually the total organic carbon flux increase to the sediments that goes up to 50% in an area of around 5 kilometers around the facilities, while on the contrary, biodeposition from fouling is a minor factor. And they've also found that the impact on gravel beds, which are within, so the green box you see here is a protected area. And you can see that the wind farms in the scenarios are planned on the edge of it. And what they found that the impact on these gravel beds in the protected area is highly sensitive to the positioning of the turbines, but not so much to the actual number of turbines placed. The last example I'm going to show you is we're going to northern Norway. A study by Wallhead et al. From 2018 about urchin harvesting and kelp regrowth. So in this case, again, physical biogeochemical projections as baseline were used to drive a kelp urchin model using, if I remember well, a size-based approach for the kelp model and a age-based approach for the urchin model. And it assessed the potential impacts of ocean acidification and warming on the urchin harvest yield. So the main outcomes here, which you also see depicted on the right-hand side in the two figures, is a 7-fold decrease in potential harvest over the next 30 years, and a requirement for annual cull or removal of urchins bigger than 10 millimeters to actually achieve a regime shift from urchin barren regime to a kelp forest. So I think these are some very interesting, powerful examples of what you can do with these modeling systems that we're trying to build to actually then inform mitigation and adaptation policy. If we then go back a little bit to the core of the problem, which is the downscaling efforts, let's take a step back again and look at the global scale. So that's where we started within Sea2Coast. We were asking ourselves, so how good are actually the global models, the ESMs, DSM projections for the regional areas that we're looking at across various variables. And we produced a lot of data across a ton of variables, or not a ton, but quite a few. So we produced these maps that you can see on the left-hand side, which are here for the Northeast Atlantic sea surface temperature. On the top of the left-hand figure, you see the present-day climatology from data, from SST satellite pictures in this case. And then you see a number of ESMs that we extracted from the CMIP6 database, compared their climatologies compared to the satellite climatology. And apart from a very different picture in between the models, you also see a lot of regional differences in the actual bias that they have. So you may imagine that in relation to your area of interest, one model may be more favorable than another. then of course biases can be corrected for. So this is the other important information that we get out from this analysis to inform our downscaling, regional dynamic downscaling efforts, is the actual biases that these ESMs produce to then be able to eliminate them for our projections. And on the right-hand side, we produce these nice Taylor plots that just summarize the figures that you see on the left-hand side. So from all these works, then we produced matrices that summarize the different statistical metrics that we computed. So what you can see here in this big matrix is on the left-hand side, the different variables at different depths. So this is temperature, salinity, nitrate, oxygen, primary production, air, sea flux of CO2, pH, dissolved inorganic carbon, and total alkalinity. And then on the x-axis, you have the series of models that we investigated. And for each pairing, you can see the correlation coefficient with a color scale going from 0 blue to 0.5. No, this is not correlation. This is spatial normalized RMSD, sorry. Going from almost 0 to 0.5 in red. And again, you can see that the picture across the different models and across the different variables is quite heterogeneous. Most models are generally quite good, but have a couple of, let's say, outliers or weak points better. And not for all models, they're in the same variable at the same depth. It's a very varying picture. So if you pick your ESN that you want to build your regional downscaling on, you have to pick it carefully and correct it well. And most of all, you can see that it's not very wise to use your ESM out of the box, certainly not for certain variables. And if you're more interested in more detail about this work, I will be giving a presentation of that at the EGU 2022 in session 3.1.4, in case you have the chance to follow there. So then from there is actually a slide missing, which I'm then just going to recapture by voice. So from there, we were working on a downscaling protocol to have a common approach to this downscaling, because the crux is that while for the global models, you have a standardized approach to the simulations that were being produced by the CMIP initiative, which is defined in the various CMIP protocols. So specifically for the scenarios, that's the scenario MIP protocol. So that's a relatively tight framework, which guarantees that the models are as comparable as possible to actually then constrain the uncertainty that is involved within these projections. Nothing like that exists at the regional level for the ocean, and particularly not for the ocean biogeochemistry. So there are some regional initiatives like CORDEX, which are, however, mainly focused on the atmospheric component. Some of them have the ocean, but if they have the ocean, they have only the ocean physics. So what we're trying here is really to align our work as close as possible to certain strategic choices, which are, for instance, the scenarios which we're gonna run, which is in order of priority: SSP 585, SSP 245, and SSP 126. But also, where possible, in terms of similar choices of boundary conditions or strategies involved for bias correction, for instance, and certainly, which is the most important on the user side of level, to provide an as common as possible set of outputs, because that's the other big problem. Then, if you have the results from your projections and they are all individual efforts, then the variables will all have different names, different types of mappings, different types of output, and so on. So we're trying to standardize that as far as possible as well. And another important impact, which is actually at the very, another important factor, which is actually at the very start of this downscaling work, is something, another factor that needs to be considered is when you pick your regional model system, you shouldn't be choosing your resolution and your domain just on the basis of your HPC resources and how much you can afford, but it should be a choice motivated by the actual questions that you're going to try to answer. And all of these factors of downscaling strategies have been summarized in a paper that was published last year, which I had the chance to contribute as well to, which is by Drankert et al. You will also find that in the reference list later, which tried to come up with a standardized procedure for designing a dynamical downscale modeling system. And I had a diagram of that in my slide, but you can find it in the paper later on. So having said that, I'm going to move on quickly to the set of different systems that we provide within CE2COAST as a dynamically downscaled system. So, and this is from the, just from the start, this is for the internal funded partners that I'm speaking now. So as Richard mentioned earlier, we have different external partners to the project as well that are happy to contribute their systems, which contribute other regions, which are Australia, which are China, some Chinese domains, and there's also the partner from PML, which has other projections for the European area. But the core areas are the ones that I'm going to present now. So we have one system for the North Sea, which is at approximately 5 kilometer resolution. I'm not going to go through the other details. The interesting point here is that the key questions that are going to be that we're trying to answer with this system is the variability of hydrodynamics, sediment transport, and biogeochemistry, and the impact of the biodeposition processes associated with wind farms, biofouling communities on the sediment and particle fluxes to the bottom. We have another system for the Black Sea, as the previous one provided by the University of Liège, which is going to be given at 3 kilometer resolution, and it's going to be looking at the variability of the Black Sea biogeochemistry processes of de-oxygenation, eutrophication, and acidification, and warming, and then going to investigate the impacts on habitat and climate regulation. Another system we have is in the Targus Estuary near Lisbon in Portugal. And there, the main questions that are going to be addressed are the changes in riverine discharges and saltwater intrusion and the related changes in habitat and flooding. The next system we have is from NIVA for the Pan-Arctic region. And in that case, they're going to look at how the biogeochemistry of the Nordic and Arctic seas are going to respond to climate change and to the loss of sea ice, with a focus on warming, acidification, light availability, changes in planktonic productivity, but also what are the implications of such changes for climate projections and for fishery stakeholders. Another system provided by NIVA is for the Hardanger Fjord. And this one will address how the Hardanger Fjord coastal region responds to climate change and potential changes in aquaculture-derived emissions, and what are the implications for regional managers and environmental agencies as stakeholders. And then there's the European Sea System, which is a two-way nested system in this case, so it's globally and on the European seas. And what we're going to look at there is which are the marine areas and habitats most affected by climate change, so which are the hotspots under multiple pressures at the European level, and also which are the least affected ones. And then we have the system that we've just seen by Veronique, the area. So this is the upwelling of Peru and Chile in the Humboldt Current. And they are looking at what is the relationship between the oxygen minimum zone and the answer, and how will it evolve under future conditions. And then there should have been the Irish system, which is here. I think I jumped over that. So this is the last one in this case, which I'm going to present. It's the Celtic Sea. And the key questions, it's at 1 kilometer scale, so relatively high resolution, and it's going to look at an assessment of key pressures, being warming, upwelling, circulation, nutrient supply, de-oxygenation, ocean acidification. And they're going to use that to inform risk assessment in fisheries and aquaculture side, but also to climate adaptation more generally at the national level. And with that, I'm going to close my presentation. I think we're going to collect the PDFs of it. So in that case, you're going to get the reference lists to this presentation within the PDF. And with that, I thank you for your attention. And most of all, I thank our funders, in my case, particularly the Italian Ministry of Education and Research. MUR. Thank you.
Thank you very much, Moma. Some very interesting examples there, very concrete as well. So certainly very interesting to see. I see some questions are coming in already. We'll address them after the last presentation. And the last presentation will be held by Rachel Cave, who's a lecturer in chemical oceanography at the National University of Ireland, Galway. And Rachel's research interests are mainly in marine biogeochemistry, with current research projects on acidification, climate change, and cycling of nutrients and trace metals in the ocean. So Rachel will talk about the fabled science policy divide, or science policy and science society divide, I should say. So the floor is yours, Rachel.
Okay, I'm just going to share my screen now, and I hope you can hear me. Okay, can you hear me clearly?
Yep.
Yeah, okay.
We can see the screen.
I can see the screen as well. Okay, just going to just check it so that I can see that. Okay, also. Okay, so well, thank you very much, first of all, for having me here, and welcome to everybody who is listening. And I hope now you can sit back and relax a little bit, because this will be a little bit gentler on the brain, this talk. You've had a lot of science up till now. But I, first of all, thank Richard, because he has introduced the idea of the co-production that is at the heart of CE2COAST. And what I wanted to talk about today is the gap that has existed between scientists and stakeholders, and how some examples of what has been good and bad about that, and then how we are addressing that in CE2COAST. Yeah. So the first thing is, here is our scientists, thrilled to bits, new and interesting, really interesting science, and they're wanting to tell the world about it. And here is our stakeholder saying, well, yeah, that's fine, but what has it got to do with me? Okay, because often the language we use is really, really distant from the concerns of our stakeholders. And then on the other side of the house, we have the stakeholder saying, here's all this stuff that I really need to know in order to run whatever my enterprise is. Maybe I am a small to medium enterprise, or maybe I'm a fish farmer, maybe I'm an NGO, so a non-governmental organization, or maybe I'm an agency of some kind. Okay. And then we have the scientist saying, oh no, that's outside my area of research, because we're very specialist. And this is kind of where we were maybe 20 years ago or so, but we've been trying to address this in the last 20 years. Okay. And also, I should mention now, before I go further, that my co-author here, Dr. Kirsten Eisensee from the IOC and UNESCO. So she's unfortunately not able to be here today, but she has also contributed to this presentation. So what I'm going to show you now then is an example of some co-production, if you like, in the early stages, and then I'll show you some more modern stuff and see where we've gone from there. And the key thing really is that if the stakeholder doesn't get the information that they need, they may go out of business. Okay, they may not be able to do whatever the enterprise is that they are aiming for. And the other thing for us scientists to bear in mind is that their taxes pay our wages. So we do have an obligation, and always have had, to do at least some of our research which is directly applicable to the stakeholders, whoever they may happen to be. And we do well to remember that. So if we think about what is driving research, okay, so for scientists, it's mostly curiosity, okay, and we have a certain skill set, and then we have some available technology, and we put that to use for our science. Our stakeholder, very often it's entrepreneurship, okay, they're setting out to do something, okay, because they want to make a living based on their skill set and what assets they have available. Maybe they have a license to run a fish farm, or they own some land, or they want to set up wind farms offshore. Okay. Scientists are also driven by publications. This is where we get our glory from, as it were. Entrepreneurship and our stakeholders are often driven by legislation, and that is whether they are a business enterprise or whether they are some kind of agency, an institution. Funding is always important. We have to have money in order to do our research, okay? And funding priorities drive some of where that funding comes from. The entrepreneur, the stakeholder, they also require an economic benefit. They have to pay their way. They have to get some wages from this, okay? And there's also then cultural practices which drive what kind of business, what kind of operation you work in. And these are something that we neglect at our peril. Also now in science, we have the metrics for promotion. It used to be just publications, but nowadays the funding priorities have changed. And so there is now, thankfully, an insistence that we engage in outreach and that we engage with stakeholders and provide some benefit to them. So we have come a long way in the last few decades on that. And government policies also drive a lot of what our stakeholders do, again, whether they are institutions or whether they are individuals or small businesses. So I'm going to start with this first example. Okay, this is about managed realignment or setback of sea defenses. Okay, and this was a project that started off around about 2000 or a little bit earlier with the Environment Agency in the United Kingdom on the Humber Estuary, a very large estuary on the west coast of the UK. They had extensive sea defenses along both banks. Okay, so they needed to because the land behind was very flat and very easy to flood from the North Sea. But these are very costly to maintain, mostly because you require rock armoring. You have to bring in huge amounts of hard rock to face the front of these sea defenses to stop the sea from eating them away and flooding all the valuable land and infrastructure behind it. So the goal then of this project was to set back the defenses in an area along the estuary. They were going to use higher ground to minimize how long these defenses were. They were able to reduce the height then, which would mean significant cost savings. It meant allowing the sea to take over some of the land that had previously been farmed, allowing developments of mudflats and salt marshes. And from an environmental point of view, there were fantastic benefits. New big area for wildlife, mudflats, salt marsh, habitats for birds and fish and invertebrates and so on. Plus, the Humber is a very nutrient-rich estuary, okay, way over what it should be. So this setback provided opportunities to trap some of the phosphate and to provide areas for nitrate reduction, so to reduce some of the nutrients in the estuary. Now this project, there was an obligation. The agency then had to get involved with local stakeholders because they were going to take over people's land. Okay, so that was the first thing. They had to negotiate with landowners. So this, if you like, was kind of a forced marriage, as it were. But they went about it very carefully because they understood that they really wanted this project to work. And they understood that it wouldn't work at all unless the local people bought into it. So this is just show you where it is. So here's the east coast of England. This is the Humber Estuary. A little bit of a telescope in here to show you where the actual site was. Okay, and this is what it looks like. Okay, so back in the day, the brown stuff here is the Humber Estuary. It's a really sediment-rich estuary. Here is the line, the green line is the old sea defenses. So that was what the sea defenses were before, and you just had mud flats in front of it. And the purple line is where they set back the sea defenses to. And prior to this setback, all of this was fields. Okay, so they set it back pretty much as far as they could without taking in the road. And there are houses and buildings and little villages scattered along the edge here. Okay, so this was the first of the projects that they did in the Humber Estuary. Okay, and it was completed in about 2003. Right, the Paul Holmes strays. And if any of you have an interest in realignment from environmental or other points of view, there's a whole series of other ones were carried out on the Humber. Okay, and there's a report, the Har Basins report, which describes all of those projects. But the first thing was the landowners, the people who owned the farmland in the area that was going to be taken over by the sea when this was set back. So lots of negotiation. And the landowners, by and large, didn't want to sell their land. So they came to an arrangement with the landowners where the government or where the agency would effectively lease the land. So it's still owned by the farmers, but there the flooding is allowed to take place. And if salt marsh develops, they will be able to graze animals on it and so on. Okay. So that was okay. So far, so good. Then we have to think about that there had been a lot of regulations over the years coming up to this to strongly encourage landowners to maintain and increase hedgerows. Okay, so for wildlife, okay. And they discovered that all of these hedgerows were going to be ripped out, okay, before this area was flooded. And they had spent, decades looking after these things, initially grumbling about having to do it, then putting them in and seeing the value. And now all that work was going to be wasted. From the Environment Agency point of view, these hedgerows had to be taken out because the minute the first tide that came into that setback, as soon as they breached the dam, every plastic bag in the estuary was going to get stuck in those hedgerows when the tide went out. And it would look dreadful. Okay, it would put off everybody who had thought this was a good idea completely, because all you would see is this big rubbish tip. Okay? This hadn't been clearly explained to the landowners, and this was almost a deal breaker as far as they were concerned. It was bad enough that they had to give up this land, even on this sort of leasing arrangement, but then to rip out all the hedgerows, what was the point of that? So that was one part of it. Okay. So this, again, had this been explained a bit better, a little bit more thought of our stakeholders, that could have been avoided. The local villagers then, and the other people who lived in the area, but who weren't necessarily giving up any of their personal land, they resisted this because they were worried about floods. This is an area that traditionally there had been floods before the sea defenses had been built. Their sea defenses used to be about 1 kilometre or more away from the dwellings. They were now maybe 100 metres away or less. Okay, so the sea was getting far closer than they were used to. They were afraid of flooding and overtopping. They still remembered 1953 when huge areas around the North Sea, both on the east coast of England and in other parts of northern mainland Europe, were really badly flooded, big loss of life. They could see there were local benefits. There was going to be a walking pathway. There'd be an increase in tourism and pub trade and so on, but they were still very dodgy about it. But one of these discussions, or some of these discussions, were held in the local pub, the EPA trying to get in sort of friendly with the locals and say that this is really going to be good. And it came up that if this scheme went ahead, there would no longer be a need to rock armor the defenses. They would be far enough back. They would have mudflats and salt marshes developing in front of them. No need to rock armor. And it was the locals then realized that they would not any longer have these big heavy lorries trundling through their village, something which had been a bone of contention for years. And that was the deal maker. They said, what? You mean we're getting rid of all these lorries? Brilliant. And that swung the argument in favor of the project. And this is just an illustration of the gap between what the research wants to do or what the agency wants to do and the actual real life concerns of the people who are on the ground involved. Okay, so that was just an example of the kind of thing and how absolutely critical it is to talk face to face with your stakeholder and find out what really matters to them, because that way then you can get on with doing whatever it is that you feel as a scientist or as an agency is important. Okay, so this had never been considered as an incentive, didn't realize it. That's it. So that's sort of on the kind of smaller and local scale. Now, in recent years, we have big networks where we are involving scientists and agencies and stakeholders. And one example which is relevant to CE2COAST is the GOA network, the Global Ocean Acidification Network. So ocean acidification is a major concern now for anybody who is involved in life in the sea at all, and particularly for all the sort of commercial fishers and shellfish aquaculture. So the goal of this project then is to understand global ocean acidification conditions. So Mama has already touched on this and to some extent Veronique, where and how fast and why it is happening. The second goal is to improve the ecosystem response to ocean acidification. What are the biological responses, how fast and where? And the third one then is to create reliable future projections of the impacts. Okay. And the critical bit here is down at the bottom, that we need to produce societally relevant forecasts and projections. Okay, we need to be able to explain to people why this matters and what's happening and what is going to happen and how we can mitigate it. We're already seeing, for example, on the west coast of the US, where those people who have shellfish aquaculture are having to add lime to their growing tanks for the juvenile shellfish so they can actually make their shells, because the seawater that's coming in is so low in pH. Okay. So this is an example, if you like, of a much bigger project than we mentioned with the Humber. This is a whole global system involving stakeholders in many, many countries to deal with a problem that is already here and is going to get worse. So the idea of this is that it provides scientific support to local and to national governments to develop ocean acidification action plans so that each government, each policy unit in each area can say, this is what our problem is here, this is what's coming, this is what we need to do to help mitigate it or deal with it. Okay. And big again, 9 regional hubs across many countries across the globe to this. And one of the things that GOAN is doing is it's providing scientific support to shellfish producers. So this is a direct link between the scientists and the stakeholders on the ground who are actually producing shellfish for market. Okay. And as well, GOAN is inputting them to the SDG at the UN Ocean Conference, okay, and also to the UN to the climate change to sort of keep this at the forefront. First of all, and help people to understand it. Ocean acidification scientifically is quite a complex problem, okay, but we need to make sure that we get the information out there so that it's clearly understood. So a third example then is the blue carbon. So this is a more recent, I guess, terminology that's come to the fore. We've been used to the idea of green carbon, where we're trying to take carbon dioxide out of the atmosphere and we store it on land by growing maybe more trees or even some of the carbon capture. The blue carbon is the equivalent for the ocean. And there are essentially 3 systems. So the salt marshes and the mangroves, for example, are 2 of the green carbon systems. So ecological systems or habitats that we think are storing considerable amounts of carbon. And again, we've got this objective. We need to describe the relevance of coastal carbon. We need to make it clear to governments and policymakers and stakeholders how important this blue carbon is. Create standards to quantify it, because we're paying now carbon. There are now carbon credits and carbon costs. Okay. Identify and support priority research. Again, carbon dynamics in coastal ecosystems. And again, this is really important because every time you try and do some research or implement a policy in the coastal zone, you're going to have to interact with the stakeholders who are already there making a living from that area. And develop the conservation, the planning, and the management guidelines for carbon activities. And again, this is a key area where stakeholders absolutely have to be involved, because it will not work if they are not. And then support development of pilot projects. And pilot projects are really important because they're able to demonstrate to stakeholders that, whatever it is policy you're trying to implement will work for them. Okay, it's not just something that's being enforced on you that's going to make you change your way of doing things. It may actually support what you do. Okay. So that's just to sort of give you an idea of the sort of from the local to the global scale of co-production between stakeholders and scientists. Okay. And one of the key successes for this is that the blue carbon projects and others have helped to reduce the loss of mangroves, okay, down from about 2% to about a 0.4% loss per year. We haven't reversed the trend. We haven't been able to increase the growth of mangroves, but at least we are reducing the loss, okay, of that. Big success in that area. So now then for CE2COAST, okay, what are we about with our co-production? Okay, so Wilma has already explained, and also Veronique and Richard, about the downscaling of global models to regional and local scales. But if we do that, if we are not presenting it in such a way as that stakeholders can see the benefit of the information that we provide from this, then we're not doing our job properly. And that's really what we're aiming for in CE2COAST. So we've been engaging with the stakeholders across all the regions, okay, to make sure that the projects is relevant to their concerns, that the actual outputs that we produce are not strings of numbers that have no meaning for stakeholders, but that have real relevance. So you've already seen this map, which shows the various areas that we're looking in, and then Mama has described also towards the end of his presentation, the various models and what they're doing. But any information we produce needs to be relevant to the stakeholders we're dealing with. So the first thing to do is, so this is just the overview of the work packages in that. The first one, the state variability and trends. So Veronique mentioned this. So to some extent, we get some of our data from our stakeholders, but the two key ones then are about the pressures on the ocean services. So what ocean services are there? What are the pressures? This is a big stakeholder issue. And then to produce outputs that are valuable both to science and society. So the first thing is to identify who your stakeholders are. Okay, so that has been done region by region. Okay, some of them are institutional stakeholders, some of them are small, medium enterprises, some of them are non-governmental organizations. Okay, then we have held stakeholder meetings in each region. Okay, for all of our local and regional model domains. Okay, and at those stakeholder meetings, we have sat down with the stakeholders and identified what they think are their key services. Okay, so this is a list now that has come up with for CE2COAST. Okay, so it's a tolerably small list, and also, of course, CE2COAST can't model everything, so we have to be reasonably constrained. But here are the main things, and the number of partners, if you like, who have an interest. Things like aquaculture, biodiversity, carbon sequestration, coastal infrastructure, fisheries, and then provisioning services, things like kelp harvesting, nutrient cycling, tourism, urchin harvesting. So there's a whole list here, but it's not a very big list. These are the key services that have been identified, and these are what CE2COAST is looking at the pressures on. So that's the first thing. What are the services? And they said this is identified by the stakeholders. This is what matters to them, not just what matters to us. The next thing then is to identify the pressures on these key services. And here the list is a bit longer, okay? But this, I said, is the summarized list from all the stakeholders. So each stakeholder will have a subset of those key services and a subset then of the pressures. But this is all of the pressures. Okay, so again, at the top of the list here, we have aquaculture. That is not only a service, it is also a pressure, because it depends on what else you're doing in your coastal waters as to whether you see aquaculture as being a positive or a negative. Climate change is a big one across all of it, okay? But there's also then a whole list of other pressures that are that. And our job then is to look at what changes in these pressures can our models address. So again, we say to our stakeholders, we can't tell you everything about all of your pressures, but from the output from our models, we can say this pressure is going to be affected in this way, and this pressure is going to be affected in that way. And that is our job, not just to model the things that we can model, but to look at our models and say, as well as the output I would expect, I can also add this, or these two outputs together can give me information about that. And that's what we're doing then, is to look at what the model will produce that actually tells us something about how these pressures are going to increase or decrease or remain the same. And then the third thing then is about the thresholds. Okay? And this again is where we need a lot of interaction with our stakeholders, because they have to be able to tell us, as well as from our other scientific knowledge, is for a given pressure, how far does it have to go in some direction before the service that it's putting pressure on is affected? So this also then is the stage where we're at now. We have gathered our key services, we have gathered information about our pressures, we're already running some of our models, but now we are going through the process of dealing with the thresholds. Okay, so we've already had a meeting with some stakeholders and some experts in developing thresholds, and now we're sort of drilling down into the nitty-gritty for each region, for each pressure. What are the thresholds that we are expecting to problems to arise at if they are not here already? So within CE2COAST, then we have embedded tasks which are related to this co-production. Okay, so the case study areas that was dealt with in relation to stakeholders, where are good case study areas. I just mentioned the thresholds and the tolerances. Again, this is something that the stakeholders can tell us about. They know that things will go wrong after a certain point. Something else we're putting in is the hotspot and refugee map. So at the end of this project, we hope to be able to say, right here and here and here are areas where we're expecting that problems are going to arise, that your pressures are going to increase significantly. Here are areas where we maybe have what we call refugia. So areas where things are not going to change, are not going to go in a negative direction, okay? Where organisms or habitats may be able to remain or expand, and maybe act as sites to reseed other habitats that have been damaged if we can bring them back. Excuse me. Okay. We are going to investigate opportunities for ecosystem management and bioeconomies. So look at economic instruments. So this is also important then from our stakeholders' point of view, because they know what some of the economic instruments and policy options are, particularly the institutional ones. Okay. And then early alert system. Again, something to deliver to our stakeholders to say, here's an early warning system for your site. So we're coordinating, identifying the stakeholders. We've done that and engaging with them. We're producing targeted outputs, okay? We're producing outputs, dissemination outputs for different target audiences. This is also key. Your stakeholders are not all the same, okay? You will have a range of different types of stakeholder in your system. We're looking at knowledge again for specific stakeholders and institutions, and then doing some gap analysis to produce integrated assessment of new knowledge. Okay, so at each of these stages, the stakeholders are very strongly involved with this and looking at what we're doing and giving it a critique so we can do it better. Okay. So then at the end of the day, you've seen this picture already in Mama's presentation. We need to provide some sort of targeted representation that's relevant to every stakeholder, to each one, okay? Not one that does for all of them. We have lots and lots of slightly generic pictograms, if you like, but we need to look at individual stakeholders and say, what sort of a thing do you need? Okay. That tells them what the services and pressures are, how the pressures are changing, how they can adapt, and incorporates the early alert system. So again, something that's actually useful to the stakeholder, but developed with their help. Okay. And the end result is that we want to end up at this, that our scientists and our stakeholder are not, talking to two different sides of the room with nothing else, but they're able at the end to say thank you to each other because both have learned. And also I like to say thank you to you for listening now.
Thank you to you, Rachel.
Okay.
Very engaging and an interesting talk. Unfortunately, I missed part of it, or at least a couple of minutes due to my internet connection just being a bit faulty here, but I'm back and I'm glad that I could see the last part of your presentation.
Okay.
I see we have some questions coming in. Perhaps we can start with your last presentation, because I see, Rachel, there is a question for you on specifically how you identify and mobilize key stakeholders where participation is perhaps more fragmented and civil society is not so well structured. And then sort of a follow-up question to that is, how do you include more traditional knowledge in your models, or is that being done?
Yeah, okay. I guess from my point of view, and Richard will probably have more to say about this than me, from the point of view of more traditional, this is back at the very beginning, I mentioned this thing about the cultural aspect of it, and that is really important for that. And it varies from country to country and region to region. But the bottom line is to talk to as many people as you can and say, this is what we're trying to do. Are you interested in getting involved? And spread the word. And not just, there's lots you can do it on things like social media, but actually to ring up people, start with a person you know and ring them up and talk to them about it and say, do you know other people? And it's a very much a human chain, because the stuff that goes out, if you like, on the sort of social media kind of thing, it reaches only a very particular part of your audience. And to get people involved, you actually have to go and ask them. Okay, and physically say, you know, Tom Smith, or whatever your name happens to be, we've heard that you're interested in this and this and this. Would you like to become involved? Okay, because people are much more likely to buy in if you actually take the time and effort to go and speak to them directly. Okay, that would be my take on that. The difficulty we have is, of course, that we are always short of time, okay, and short of people. And it takes a lot of time and a lot of human energy to do that. But the value of it is incalculable. It's really, really, really well worth doing. in a small country such as Ireland, where I am, where we are in this sort of everybody knows everybody space, so that helps a great deal, because the person who runs the institution or the agency also has a brother who is, you know, a fish farmer or something. There's a real link. It's maybe harder in more fragmented communities, and particularly where you maybe have divided communities, where if A is doing it, B won't, and that sort of thing. And also maybe where you have more, perhaps a bigger country, and things are a bit more formal. So in smaller countries, you very often are able to have much more informal arrangements, and that gets more stakeholders on board because they don't feel so pressured by it. So I don't know if Richard maybe wants to add something to that.
No, I support everything you said. I think that you start from the ones that you work with already, but that shouldn't last for very long. That's the seeding that Rachel was referring to, that you ask the stakeholders, you go through their networks, you identify the local for example, in Norway, we use the local fisheries union member to then communicate further and further. We go through the national, the county council and the local council level to use their people who are responsible for management and also the environmental stages, and they will nominate people. So it's quite quickly not coming from the scientists. It's very important that it evolves organically with other people recognizing the relevance of the science through their networks. But at the same scale, we also go through the departmental and environment agency levels in Norway to facilitate this as well. So you end up initially with a big group. The kickoffs are much more populated. We suffer a lot from stakeholder fatigue, and especially when stakeholders are in every proposal now, or every project, that people are dying off. Not literally, but from the project. So another way which we're approaching that now, thinking for new projects, is that we are actually paying them to be on there. The key stakeholders have a strategic role, whether scientific or stakeholder management role, and that we hope will work much better. And going back to how local communities, that's on two different levels. One, I and others have given open house presentations in the local towns which are closest to our services. We would just put a sticker up on a telegraph pole or advertise it through a local newspaper, and you go and give a presentation in the evening and you have no idea who's going to be there. And you get some very good feedback. And a good example of that, I don't want to use all the time, we do have a few more questions, but following up to Rachel's seawall example, is that within 3 years of a Norwegian coastal change project, the law was changed. And that usually takes many, many years. And that was very much to do with this communication of scientific terminology, first of all, understanding their needs, sampling where they said we should sample, not where we would traditionally sample, a communication of what the models meant, an evaluation, a shared evaluation of the model output identified that the source of acidification and de-oxygenation and eutrophication, so too much productivity in the surface waters, was due to land use and grey water supply from the town. And within 3 years, the laws were changed for grey water release to the fjord. So that would change the local physics, change the local organic material supply. And they could see that this was going to reduce their sensitivity to ocean acidification and oxygen and de-oxygenation. But that was because we had been talking to the locals, and it was pressure through the newspapers that made the politicians change so quickly. So that's a very good way. So how can local communities be involved in the models was one question by Antonio Pedro. That's a very good example of using public, well, no, not using public opinion, but informing public opinion so that they can have a more informed say towards the politicians.
Maybe a related question to that from Carlos Sousa in Brazil, asking how you can engage stakeholders when the political landscape is not always welcoming the idea of climate change, as is the case in Brazil right now. Any ideas, any thoughts?
Without naming any countries, I have worked with certain countries in Asia and Southeast Asia where that is a very telling challenge. But again, it doesn't affect the communication of science. You can talk to the fisheries, you can talk to the services, but there is an understanding that the decision making is a very different process. But I don't think it should stop anybody going through our process or a similar process in having discussions at local levels. Even if the government doesn't believe in what is changed, then it just means that the change will take a little bit longer. But again, if you inform public opinion, then we should all hope that in the end change will come.
Sometimes terminology is important. If you can find other words to use that don't sort of trigger the reaction that climate change sometimes does. And also if you're asking the stakeholders about what changes they have seen in their lifetime, that can be a nice way to lead into it. And, you know, my grandfather remembers all this kind of thing. It's about triggering people's memories to think, actually, it wasn't quite the same when I was a kid, or, you know, my dad, and that you don't have to call it climate change if they're not comfortable with that. But just, you know, change, or, you know, that the system is altering or moving or migrating or evolving in some way, that can be enough just to kind of get over that issue with it. And the thing is to respect people's lives and memories and how they brought up. And that's really important. I think if stakeholders feel they're not respected, and scientists are, you know, think we are so arrogant and we know it all, you just shut the door. And we have no right to do that. So we need to approach it gently when there are difficulties like that.
That's some very good advice there. Thank you. We have some additional questions for Veronique. I can't see her here present anymore, but I'll perhaps ask them, and then Richard or anyone else, if you can respond. So first of all, from Antonio Pedro as well, do you have data on ocean de-oxygenation in the Benguela current? Is there any data there?
Anybody want to take that? I can do it, but I mean, certainly University of Cape Town and also the Germans outside of this project have, it's not one of our study areas, but there's an awful lot of research on de-oxygenation, and also the timing of the de-oxygenation events causing the shrimps and the fish to swim onto the beach and die. So there's an awful lot of data, and it's a strong part of this international oxygen consortium that Veronique talked about. And then the second point, Anthony Clark, about to Veronique about de-oxygenation and coastal biodiversity. It wasn't mentioned during the talk, but the main services which are being studied in that region and the sea to coast is the lobster harvesting, which is very important to the islands there. and they've had some very constructive stakeholder meetings looking at the timing and the depth of de-oxygenation events onto land or onto the near coast, not onto land, but towards land, affecting the lobster fisheries there. So yes.
Okay, thank you very much, Richard. We have also received some questions through WhatsApp, which have been sent here through the chat. One is from Mariame from Côte d'Ivoire, referring to the current lack of data in the Gulf of Guinea. And she says that the models do not really reflect exactly what happens on the ground. So she asks, how can we understand these local changes without reliable data? Do you have any way of helping her?
Yeah. I don't want to speak all the time. I can answer it, but anybody want to jump in? I mean, field data is needed anywhere. Even if there is a lot of data, there's never enough data. So what we have done in the past and what we are promoting through Sea2Coast and other projects is that you can use the trends from the either directly from the CMIP6 global models closest to your observations, and use your observations to adjust. So yes, the models are very, very likely wrong in your region, but maybe the trends are reasonable. So you can actually adjust the value that you can get from the nearest model data, and then it's called delta change. So you just actually normalize the model data to your observations, and then you use that to project how it may change into the future. It's not as strong, but we use it in certain fjord regions in Norway where we don't model. So it's not just a problem where you have little data, it's also where we have little model understanding that you can combine these two. So ground truthing it with whatever observations you have is much stronger than taking anything from the IPCC generally.
Yeah, thank you, Richard. And related question from Mariame as well is how developing countries can participate in model downscaling if they don't really have robust data centers. Or is there anyone else who would like to respond?
I don't know, maybe Momo knows more about data handling and how it can be dealt with. Yeah.
Well, they can certainly contribute even if they don't have the capacity to run their own models. They can dedicate their efforts to analyzing them and bring in their local knowledge. So they might have a much better detailed knowledge of the system, of the actual natural system in place to validate those models that bigger centers and more engaged countries run for their areas, and feedback to them. Get in touch with the scientists that are running these models and feedback their results from their analysis and engage in the process of improving them. And most of all, of informing them of what's going on with the models in those areas.
With that also is to join the international networks, join the Ocean Acidification Network, GOON, or the Oxygen Network, the Global Oxygen Network. Here you can interact with other scientists, combine, they have dedicated data groups which are experts on integrating your data into the global data sets, or they can identify other data sets which may be useful to inform your particular area.
Slightly related questions, or from Gerald in France. basically talking about the limitations of the models. Gerald says basically models are always inherently wrong, and asks how you can explain data gaps and uncertainty specifically to stakeholders and policymakers, and then still get them involved.
Go on, Mama, you're the modeler here.
Well, that's always the problem, is always to get people on board to trust at least some parts of your modeling systems, because the first thing you have to communicate is an uncertainty. And if you communicate that only negatively, then very soon you lose people. But actually, it's an added value. It's an added information. It's everybody knows about that for weather reporting. Nobody accepts it, or very few people accept it for climate projection. If you see the weather report, you know this is just a guess. But still, you'd like to know if the sun is shining tomorrow or not. And so it's a way of communicating things in the right way, and at the same time, be honest about it, but also in a positive way. Often we scientists, and particularly I find us modelers, we tend to be negative about our results in terms of that we know all the weaknesses that they may have, and focus on them because that's what we work to improve on. But then actually there's a lot of things that they do pretty well and they do pretty right, and you should be honest about that as well. And as I've been showing before when I was talking about uncertainty in my talk, yes, there is a considerable uncertainty in primary production at the global scale in the current set of models. But I've also shown that they are restricted to essentially up to, I think, about in between 90 and 100% in two areas of the globe, which is the Indo-Pacific and the North Atlantic. That means for the other regions, the uncertainty is actually pretty low. So it's all a matter of getting the right information out in the right way. And there we all have to become smarter, I think, in communicating to the general public.
Yes,
and to our policy stakeholders.
Just to add one thing as well, it's also sometimes good to say to people, look, here's the model output. And we've done this because we know it's not perfect, but we are using it to find what it is that we need to measure. We use the model sometimes to find out what we're missing as much as to sort of say what's going on. Sometimes we say, okay, we're modeling the system. We know it's not right. And then when we have produced the model, we understand, this is where the gap is. And it's because we don't have information about, whatever, the carbon dioxide or the phosphate or something like that. But the model is often used to tell us what it is we have missed, if you like, in our monitoring or in our understanding. So sometimes if it can be presented in that way, to say we're using this as a tool to figure out what it is we don't understand, as opposed to saying, the model here, and here is the answer. Sometimes the model is just a tool to help us grasp what's missing.
Yeah, thank you, Rachel. I think that's very clear. So we have another question from Jérôme Benveniste, sorry, asking about satellite data. What kind of satellite data are you using? And how much more and what kind do you plan to use, or would you ideally need? Anyone who wants to take the question immediately?
I can say something then, just to be polite. I think, the satellite data is independently used because it goes through the Siemens European, the data set, which is used to inform on some of the modeling that comes from Siemens that we're using, especially for work package 1 on the data trends and variability. We also, certainly in the North Atlantic and the Arctic, which is contributing to CE2COAST, I have a PhD student looking at acidification from space with our partners, Plymouth Marine Laboratory and the University of Exeter. where we're determining salinity from space and using local alkalinity algorithms, and using and calculating the partial pressure of CO2 from temperature and salinity, testing different algorithm opportunities. So yes, we are using salinity data to some degree, but it's not specifically written into the proposal. But it is coming through our collaborations.
Okay, thank you. I think we can have one last question, and I see here another question from Sandra Clough, asking about top-down effects on de-oxygenation. She refers to an example in Mauritania where small pelagic fish reserves are overexploited due to fish meal factories, and these then still pollute or also pollute coastal waters with outflow. Not 100% sure what the question is, but will these top-down effects then be? I assume these are not included in your models. Would you like to add anything there?
It is used. You saw in Rachel's presentation that aquaculture became a stressor. Then there is a top-down influence, which we are modeling through the local fjord model that's coming from NIVA, which is assessing the carrying capacity of the fjord and its sensitivity to salmon farming. So yes, the release of the release of organic material directly from salmon farming, but also from feed loss and the oxygen demand that has on the intermediate and deep fjord, then yes, we are addressing it. I'm not sure about other groups. So yes, we're doing something analogous to that question.
All right. I think we have to close. I know some of you will have to or have other meetings planned now. And I think Richard will need some rest as well, recovering still. So thank you very much from my side. It's been really an engaging event, super interesting presentations, very informative also for me, as I hadn't seen these latest results of the project. Very concrete examples, which I personally really like as well in these sort of presentations. So thanks to you, to all the speakers, thanks to the audience for the questions. And I hope we'll get an update or perhaps in a next session when the project is close to the end for the final results. So thank you and have a nice afternoon, everyone, or nice evening, morning.
Thanks.
Thank you for comparing.
Yeah, thank you.
Thanks for joining.
Okay.
Bye-bye.
Goodbye, everyone.
Okay. Bye-bye. Bye-bye.